So we figured out a way to deal with the constant multiple, and the power rules, and also x, so any lines and things like that. So now we want to find the derivative of f of x equals 3x squared minus 5x. So that has a sum in it, right? Multiple terms. So if it has multiple terms, what do? Well, we've actually learned this derivative already. The derivative of this is 6x minus 5. And you'll notice what we're doing is we're using the power rule for each term. Power rule and actually the constant multiple rule for each term separately. And that's the sum rule. Namely that if you add and actually subtract as well, that it doesn't make any difference. You just take each term as it comes and find the derivative of each part. So I know it says sum rule, but I should also say and difference because it works for subtraction just as easily as it works for addition. So it could work for plus or minus, which makes it on our sheet, it's actually rule number 5. U is f of x, v is g of x, and so therefore the derivative is the derivative of the first one plus or minus the derivative of the second one. It's right there. So it's rule number 5, but we're using u's and v's, which is actually kind of more useful in the long term than f and g, but there you have it. Right? So right here, this is rule number 5. Rule So it's that if I want to take the derivative of u plus or minus v prime, right, derivative, that would be u prime plus or minus v prime. Same rule. Okay, so that means that taking derivatives of polynomials, because polynomials are just stringing together terms of constants and multiples of constant multiples of variables. That means we should be able to take the derivative of these very, very quickly. And we can. So this is saying that if I want g prime of w, right, the derivative of this, which for the record would be d over dw of g of w, right? That would be how you'd write it in Leibniz notation. Take the derivative with respect to w of that function of w. That would be, all right, bring the power down. 3 comes down. 2 times 3 makes 6. W to the 3 take away 1 is 2. Plus, bring the power down. So 9 times 2 is 18. W to the 2 take away 1, which is 1. Minus, okay, so this one you can think of a couple ways. 16w, this is w to the 1 power. They don't put it there, but it is. So if it's w to the 1 power, you could bring the 1 down, 16w to the 0. Or you could remember that the derivative of any line, linear term, is the slope, right? So if you have 16x, the derivative is 16. So it's this it's either the linear rule, if you want to think of it that way, or the power rule. The linear rule is actually just a case of the power rule. The power rule is the more important thing. And the derivative of 21 is, of course, 0. Now, you don't have to write the 1 here if you don't want to, because we generally don't write 1s for powers because we're lazy, but nevertheless, it's there. So if you want to write the 1 or do not want to write the 1, either way, it's all fine. All right, so let's find the derivative of s of t, if s of t is this function. So s prime of t would be equal to, which is also ds dt, derivative of the s function with respect to t, if you want to write it. This is Bernoulli notation, kind of Newton-Bernoulli, and this is Leibniz notation. All right, so I would multiply 2 times negative 9.81, which is negative 19.62. Right? 2 times 1 is 2, 2 times 8 is 16, yada yada, right? T to the 2 take away 1 plus 43.2, right? That's a constant times t. The t is to the 1 power, so you 43.2 times 1, t to the 0 is as a constant. So it's again that linear term, right? 16w became 16, 43.2t becomes just 43.2, and then plus nothing because the derivative of 91.62, since that's constant, is 0. And we're done. So that means that we can easily compute derivatives quite simply, even when the constants are not integers, even when they're decimals, even when they're fractions, all that good stuff. So even when the constants are not integers, and actually even when the powers are not integers, because we saw that with fractions and with fractions and radicals, it worked out nice and easily. Now you might be tempted to use the power rule for exponents. So for something that looks like e to the x. So let me just give you some examples. So f of x equals e to the x, or g of x equals 7 to the x, or h of x equals, let me think, pi to the x. Ah, sneaky. Right, so you might be tempted to use this power rule, and a lot of students are. A lot of students try to use the power rule for functions like this, and that would be a problem. That is not correct. See, the power rule is, let me just rewrite the power rule real quick. The power rule says if you take the derivative with respect to x of x to the n, right? X is the variable, n is a power. That would be equal to nx to the n take away 1. So the issue here is that where's the variable on these ones? So you'll notice the variable is not in the base. The variable's in the exponent. Here, variable's in the base, and it's raised to an exponent. It's raised to a power. So this is the variable's the base. That's what that's called, if you remember from learning about exponentials in algebra class. And the n is the power, right? N, which is constant, is a power. Exponential functions don't work like that. Exponential functions have the constant as the base. And the variable is to the power, right? So the base is constant, right? So you could think of it as this way. I'm taking n to the x, right? So I'll call that, I don't know, k of x. So if I have n to the x, so the base is constant, and the variable is the exponent. And that's a very different situation because that's not going to work the way that the powers work, because the power rule is saying, hey, if I have the variable in my base, then I can just deal with my power. So this is a power function. So in algebra class, when we first start talking about powers and exponentials, we kind of use the words interchangeably. But for us in calculus, we actually want to make a distinction between these two kinds of functions because they're not the same. Exponential functions have the variable in the exponent, and their derivatives are very different than power functions. Power functions are the things we use to make polynomials. So you have your x and you're raising it to the 3, raising it to the 7, raising it to the pi. I mean, I don't care, right? Any of those would be a power function. So this is easy. We can do this with the power rule. This is actually, well, some of these are easy, e to the x. Some of them are a little bit more complicated, but they actually have their own rule. And let me pull that rule up here. This is just a reminder of what the definition of Euler's number is, just as a little review. I think I should actually flip this page around and put this in front of what I just talked about, but that's all right. So this leads to amazing fact. Euler's number, right? E is about 2.71828 and some change. It's like pi. It's a number that has no repeating pattern and has lots of special properties, etc. And the derivative of e to the x, now I'm not dealing with the 7 to the x and the pi to the x yet. The rule for those is coming. But right now I'm just dealing with this one, right? The e to the x, the natural exponent, Euler's number. The rest of these will come soon in another section. But the derivative of e to the x is lovely because the derivative of e to the x is e to the x. It is its own derivative, which is just absolutely fabulous. So let me prove it to you real quickly with Desmos. So, there's my YouTube channel. So if I go in here and I make it, instead of x cubed, I make it equal to e to the x. There's the function. Let me show you the derivative. In fact, I don't know if it will. There it is. Function, derivative, right? So it's the same thing. You see it? Oh, you probably can't because it's so close to the same color. And let me switch my derivative graph to like orange or something so you guys can really see it. Okay, so there it is. There's the derivative. There's the function. There's the derivative. There's the function, right? So e to the x is its own derivative. It's a really nice derivative. We love it because it's so simple. Well, that means that taking derivatives with e to the x is going to be easy peasy. So if I want to find the derivative of this function, e to the x plus 14 e to the x minus 3x to the 2/3. So that's a little tricky. We might want to notice these two are like terms, right? So we can combine them together for our own benefit and make it 15 e to the x minus 3/2 x, minus 3, excuse me, minus 3 x to the 2/3. There we go. So there's that function. So then the derivative would be super simple. It's 15 e to the x because the derivative of e to the x is e to the x. And then for this part, we would use the power rule. See, this is exponential. This is power. So for this one, I'll use the power rule. For this one, I'll use the e to the x rule. So for the back one, I would say 3 times 2/3 x to the 2/3 take away 1, which would be 15 e to the x take away 2 x to the negative 1/3. That's not technically simplified. To simplify it, I would have to write it 15 e to the x minus 2 over x to the 1/3 power. Again, I don't care that much about simplification all the time, but if you need to simplify it, that's how to do it. So knowing that derivative that we just found helps us find the equation of a line that is tangent to that same function. So remember that the equation of a tangent line, well actually any line, but a tangent line in particular, is y minus f of a equals f prime of a, because that's the slope of the tangent, times x minus a. We learned that in section 3.1. So from section 3.1, we learned this. Okay, so let's think about this. The derivative that we just found for the example above will help us get f prime of a. F prime of a. And here they're telling us that x equals 1, so a is 1. So I'll be able to put 1 in right there. Now I'm going to need both f prime of a and f of a as my two function values. So because I'm going to need both of them in order to be able to find this. So let me start off with saying if a is equal to 1, let's find f of a. F of a, I'm going to do it in a different color, sorry. F of a is equal to e to the 1, plus 14 e to the 1, I'll just do this, minus 3 times 1 to the 2/3. But that would be 15e, I forgot about my simplification there, minus 3. Okay, so there you have it. I mean, that's an exact answer. So that's f of a right there. So that's what's going to go in right here. And then a equals 1 is going to go in right here. And so then I just have to figure out the derivative part. Oh, but I already have, right? The derivative's up here. Matter of fact, right here. So if I want f prime at 1, because that will be the slope of my tangent line, by definition, derivative is the slope of the tangent. That would be equal to 15 times e to the 1 minus 2 over 1 to the 1/3. Okay, so that's 15e take away 2. Ugly, I know, but it's true. All right, so then my function is y minus, and then parentheses, 15e take away 3 equals, and then my m, which is 15e take away 2 times, parentheses, x minus 1. because that was my A value. And that is technically the correct answer, and we're done right there. This is an exact answer. Now we could simplify it a little bit. We could distribute our negative and FOIL this out and kind of deal with this, but we don't have to. Nobody said. And now if we wanted to do decimals, we could. So I could find what 15e is in a calculator, and 15e minus 3 and 15e minus 2. And when I do that, I get a decimal approximation. So this would be the decimal approximation. This would be exact. Of course, exact is our default. So we assume in calculus that we're being asked for exact answers unless we're specifically told otherwise, or quite frankly, unless it's a story problem or physics problem, because usually in physics problems we allow for decimals.